It seems like everywhere you look these days, AI is popping up, right? Like every time you open the news, there's another story about AI doing something incredible.
Yeah, it's definitely having a moment.
And one of the fields where it's been making some pretty big waves is mathematics, something that we used to think of as like the ultimate human thing.
Yeah, for sure.
But are these AI systems really as smart as the hype suggests?
Well, that's a good question.
Today, we're going to dig into that, focusing on how these so-called large language models actually perform when faced with some of the toughest math problems out there.
Okay.
We're talking about the 2025 USAMO.
The USA Mathematical Olympiad?
Exactly.
That's a seriously challenging competition.
It is. It's not just about crunching numbers and getting a final answer. It's about proving your solution step by step with rigorous logic.
Right, like showing your work, but on a whole other level.
Right, exactly. And the research we're looking at today really puts these LLMs to the test, pushing them to see if they can actually reason mathematically and construct valid proofs.
This is way beyond just getting the right answer.
Exactly. It's about understanding the why, the deep underlying principles. And to guide us through this fascinating world, we have our resident expert back with us.
Always happy to be here.
So before we dive into the nitty-gritty of the USAMO challenge, let's set the stage a little bit. We've seen some headlines about these models doing really well on certain math benchmarks, right?
That's right. There was that MathArena evaluation where some models showed they could perform comparably to top human competitors on the AIME.
The American Invitational Mathematics Examination.
Yeah, that's a pretty impressive feat, right?
It does sound impressive.
But there's a key distinction that the researchers in this paper bring up.
Okay, what's that?
The AIME and a lot of similar math competitions, they mainly focus on getting that final numerical answer.
Got it.
So even if a model can arrive at the correct answer, it doesn't necessarily mean it understands the math behind it or that it could explain its reasoning in a way that would satisfy a mathematician.
So it's like being able to solve a puzzle without knowing why the pieces fit together the way they do.
Exactly.
And that's where the USAMO comes in, right?
Precisely.
It forces these models to go beyond just finding the answer and actually demonstrate their reasoning. So tell us more about how they set up this USAMO challenge.
All right, so they took the 6 problems from the 2025 USAMO.
And these are brand new problems, right?
That's right, the model hadn't seen them before.
Okay.
And then they had 6 of the leading reasoning models take a crack at them.
So the big names, the ones that are supposed to be really good at this kind of thing.
Yeah, models like QWQ, R1, Flash Thinking, O1 Pro,
Okay.
O3 Mini, the one we mentioned earlier that did well in the AIME,
Right.
and Claude 3.7.
Okay, so a pretty solid lineup. And to make sure they really tested them thoroughly, each model tried to solve all 6 problems.
Yep, and each problem was attempted 4 separate times by each model.
Wow, that's a lot of attempts.
It is.
So with all that effort, did any of these models manage to impress on the USAMO?
Well, that's where things get interesting. The researchers found that all the models performed, to put it mildly, very poorly.
Very poorly, like how poorly?
Across almost 150 attempts, the average score was less than 5%.
Less than 5%.
Yeah, and what's even more striking is that not a single model got a perfect score on any of the problems.
Wow. So they didn't just underperform, they basically failed?
Pretty much. The researchers were pretty blunt about it, saying that this suggests current LLMs are fundamentally not up to the task when it comes to this level of mathematical reasoning.
Okay, so that's pretty clear. They're not ready for the USAMO. But what's more interesting to me is why? Why did they fail so miserably?
That's the million-dollar question.
Right, exactly. The researchers did a deep dive into the generated solutions, really trying to understand the types of errors models were making. And they had some real experts on hand to help with this analysis, right?
Oh, yeah, they had former IMO team members and people who had been involved in the final stages of IMO selection, so they really knew their stuff.
So what did these experts uncover?
Well, they identified several common types of errors that shed some light on how these models are thinking, or rather, where their thinking goes wrong.
Okay, tell me more. What kind of mistakes were they making?
One of the most frequent issues was what they called flawed logic.
Flawed logic.
So this includes things like using unjustified reasoning, connecting steps in a proof with incorrect rationale, or misinterpreting what they've already figured out.
Okay.
Like, for example, there was one case with Claude 3.7 where it correctly proved something for a single index in a problem.
Okay.
But then it went on to say that this was true for all indices without giving any reason why.
So it just assumed it could generalize without any justification.
Exactly. It was a clear logical leap that wasn't backed up by any sound reasoning.
That's kind of a rookie mistake, isn't it? You can't just assume something holds true in all cases just because it worked in one specific instance.
Right.
What else did they find?
Another big one, but that unjustified assumptions.
Okay, so they were just taking things for granted without proving them.
Pretty much. They would treat crucial steps in a proof as if they were obvious or trivial. skipping over the necessary explanations that a human mathematician would provide.
Interesting.
For instance, in one geometry problem, O3 Manai made an assumption about the position of a point relative to a circumcircle without giving any reason why that assumption was valid.
So they're building their arguments on shaky ground, potentially leading to completely wrong conclusions.
Precisely.
What other patterns did they notice?
Well, they also talked about a lack of creativity in the model's approaches.
Okay, so they were being kind of unimaginative in how they tried to solve the problems.
Yeah, basically, they would often get stuck on one particular approach, usually an incorrect one, and just keep trying the same thing over and over again.
So they weren't able to step back and consider other possibilities, maybe try a different angle.
Not really. They lack that flexibility that's so essential for human mathematical problem solving.
That reminds me of when I was learning to code. I would get so focused on one way of doing something that I'd completely miss a much simpler solution.
Yeah, I can definitely relate to that.
The paper did mention one model, flash thinking, that seemed to be a bit of an exception in this regard.
Right.
Did it actually show some creativity?
Well, it did try multiple different strategies within the single attempt,
Okay.
but the research pointed out that this exploration was often pretty superficial.
So it was more like trying things at random rather than systematically exploring different possibilities?
Yeah, exactly. It lacked that depth of investigation that usually leads to real breakthroughs.
Okay, so it sounds like genuine mathematical creativity is still a big hurdle for these models. Now, the paper also discusses something called artifacts from training.
Right.
What does that mean in this context?
Basically, these are errors or tendencies that seem to stem directly from how the models are trained. Okay. One prominent example is something called answer boxing.
Answer boxing. That sounds interesting. Tell me more.
Okay, so a lot of these models are trained using reinforcement learning.
And that's where they learn by getting rewards for certain outputs, right?
Exactly. And one thing they're often rewarded for is providing a clearly identifiable final answer, usually enclosed in a specific format.
Got it.
So what happens is that these models get so focused on producing this neatly boxed answer that they sometimes force their reasoning to get there, even if it doesn't make sense or it leads to wrong conclusions.
So it's like they're so obsessed with putting everything in a nice little box that they end up squeezing things in that don't belong.
That's a good way to put it.
Do you have an example of how this answer boxing actually led to errors?
Yeah, there's a pretty clear example with the QWQ model. In one problem, it figured out that all even positive integers satisfied the given conditions.
Okay, so it got that part right.
It did, but then because it was so fixated on providing a single boxed answer, it rejected the idea of a set of solutions and just said the answer was 2.
Oh, wow. So it actually went against its own correct reasoning just to fit this answer boxing behavior.
Yeah, it's kind of ironic. It shows how the training process, in some ways, can also create these unintended biases that actually hinder their ability to handle more complex problems.
That makes sense. What other training artifact did they observe?
Another one was the tendency to overgeneralize patterns.
Overgeneralized patterns.
So the models would see a pattern in a few small examples and then just assume that this pattern would hold true in all cases without actually proving it.
So they were jumping to conclusions based on limited evidence.
Yeah, they were lacking that rigor that's so crucial in mathematics.
Right. You can't just assume a pattern continues forever without solid proof.
Exactly. They were good at spotting superficial patterns, but didn't have the deeper understanding to know when those patterns were actually mathematically valid.
Interesting. Did the researchers find any other types of errors?
They did. They also noted some instances of plain old algebraic and arithmetic mistakes, though these were less common.
Okay.
And they looked at the overall structure and clarity of the solutions, finding that some models, like the ones from OpenAI, tended to produce more coherent and logically organized responses.
So some were better at explaining themselves than others. But even the ones that were better at explaining themselves were still getting the answers wrong?
That's right.
Now, I read that the researchers tried to use LLMs to automatically grade the generated solutions.
Yeah, they were curious to see if they could automate the evaluation process.
So how did that go? Did they create a robot math teacher?
Not quite. They used 2 of the models, O3 Manai and Claude 3.7, to try and grade the solutions based on rubrics and example solutions created by human experts.
Okay.
But it didn't work out so well.
What happened?
Both LLM graders ended up being way too lenient.
So they were giving out A's for effort even when the effort was totally wrong.
Pretty much. They were awarding points for reasoning that was either incorrect or completely unjustified, leading to a huge inflation of scores.
How huge are we talking?
In some cases, the scores were up to 20 times higher than what the human experts gave.
20 times higher.
Yeah.
So the same models that struggled to solve the problems were also terrible at judging whether a solution was actually correct.
Exactly. It's kind of a double whammy. It shows that being able to generate a seemingly coherent explanation doesn't necessarily mean you understand the underlying math or can evaluate the logic of a proof.
It's like someone writing a beautiful essay about a topic they completely misunderstand. It might sound impressive at first, but once you actually know the subject, you realize it's full of errors.
That's a great analogy.
So this whole deep dive has really challenged the idea that LLMs are about to become math whizzes, especially when we're talking about the kind of rigorous, proof-based reasoning that's required for something like the USAMO.
Yeah, it's definitely a reality check.
And this emphasis on proof actually brings us to what I wanted to explore in more depth today.
Oh, and what's that?
It's the whole question of innovation, or maybe the lack of innovation in the way these models approach these problems.
Yeah, that's a really interesting point.
When we look at why these models had such a hard time with proof-based problems, it suggests that there's a deeper limitation in how they're currently approaching mathematical reasoning.
Right. True mathematical innovation often requires a lot of creativity, intuition, and the ability to come up with completely new ways of thinking about a problem.
And those are exactly the areas where the models seem to fall short. They weren't coming up with clever new proof techniques. They weren't spotting unexpected connections. They weren't making those insightful leaps that human mathematicians often do.
Exactly. It's like they were stuck in a very narrow way of thinking, almost like following a recipe without really understanding the ingredients.
And it makes you wonder if the way they're being trained is actually preventing them from developing this kind of deep mathematical understanding.
Yeah, it's possible they're being rewarded for getting the right answer, but maybe not for understanding why the answer is right or for exploring different ways of getting there.
It's like training someone to play a specific song on the piano perfectly, but then expecting them to compose a whole new symphony.
Ex-
They might have the technical skills, but they lack that creative spark.
And that creative spark, that ability to think outside the box and come up with truly novel ideas, that's what drives real mathematical progress.
And it sounds like that's what's still missing from these models.
Yeah, for now at least.
So, to sum up this deep dive, while LLMs are definitely powerful tools, they're still far from being able to handle the kind of deep mathematical thinking that's required for high-level competitions like the USAMO.
Absolutely. Their struggles with logic, assumptions, creativity, and the way they're trained all highlight the gap that still exists between their abilities and those of human mathematicians.
And the fact that they couldn't even accurately grade their own solutions shows just how much work still needs to be done.
It's a humbling reminder that true mathematical understanding is a complex and nuanced thing.
And it raises some fascinating questions about the future role of AI in mathematics.
Yeah, like if these models are struggling so much with the creative aspects of proof and innovation, how can we change their architecture and training to help them develop those abilities?
That's a big question. And it's one that researchers are actively exploring.
For sure.
Well, that's all the time we have for today, but we'd love to hear your thoughts. What do you think about these findings? What are the implications for the future of AI in math research and education?
Yeah, leave a comment, let us know.
And if you want to learn more, we encourage you to check out the original research paper. It's a fascinating read.
It really is.
Thanks for joining us for this deep dive.
Until next time.
See ya.